In this video, I'm going to cover AM all the way from the discovery of radio waves to building your own AM radio transmitter. Heinrich Hertz was the first scientist to successfully generate and receive electromagnetic waves. He did it by creating voltages high enough to create some sparks, and the sparks emitted electromagnetic waves of all kinds of frequencies. When these bursts of electromagnetic radiation reached a receiving spark gap, another spark appeared. This experiment was pretty crude, but it was the first time anyone had communicated information via radio waves. You can replicate the experiment right at home with an AM radio and a light switch. Just tune the radio to a quiet station and flip the light switch on and off. The little sparks generated when you flip the mechanical switch create a little burst of electromagnetic radiation, and your AM radio detects it as a little popping noise. A few years later, Nikola Tesla created radio transmitters and receivers that could be tuned to different frequencies, so many people could transmit and receive information at the same time without interference. He accomplished this by creating a transmitter that was essentially a high-voltage oscillator with an adjustable frequency, and his receiver was basically a well-tuned LC filter which rejected all unwanted radio waves and allowed you to listen to the radio transmission you wanted. This system led to the development of telegraph machines that were used all around the world. And again, you can do similar experiments at home very easily. Instead of making Tesla coils or LC-based oscillators, here's a schematic for an oscillator built out of an op-amp chip. It'll spit out a wave from 300 kHz to 1.2 MHz, and this covers most of the AM radio spectrum. If I adjust the potentiometer, I can change the output frequency I transmit on. By the way, this circuit won't work with low-speed op-amps like the LM741 or LM324. The op-amp I used is a TL072BCN that I got from DigiKey. The critical specs here are a gain bandwidth product of 4 MHz and a slew rate of 14 volts per microsecond. The op-amp you use will have to have similar specs or better so that it can operate as an oscillator well into the megahertz range. It will also have to be able to handle at least 9 volts. Okay, so you've got your oscillator. Now if you add a long piece of wire to the output of the oscillator, at least 1 meter long, some of the energy from the oscillations will be converted to radio waves, and you'll have a very crude radio transmitter. By the way, you always want a capacitor before your antenna to protect your circuit and block any DC voltages the antenna may accidentally touch. Now I'm almost ready to show you a simple telegraph, but first you'll have to bear with me. I live near a broadcasting tower, and there's no way for me to get total radio silence on this cheap little radio. So if you hear a boring news broadcast, just pretend that it's white noise from an empty station. Right now the AM radio spectrum around me seems quietest around 900 kHz. So let's see what happens when I adjust the frequency of my oscillator to around 900 kHz. At 950 kHz, you'll notice that the receiver goes totally silent. That's because it's detecting the radio waves that I'm transmitting instead of picking up random noise. Now this is where the fun starts. If I put a switch on the 9-volt supply line, I can turn the oscillator on and off, which will cause the waves to be transmitted in little pulses. So now I can tap things out in Morse code, and somebody tuned into the same frequency can listen. The modern term for this is on-off keying, because the only thing I'm doing is turning the oscillator on and off, and sending out radio waves in little pulses. Okay, now what is AM? AM is amplitude modulation, and I should probably explain what modulation is. You know how we started out by transmitting a wave of 950 kHz and the receiver detected it? That wave is called the carrier wave, and it's typically of a high frequency, anywhere from 100 kHz to 10 GHz and beyond. That carrier wave, on its own, isn't really useful for any kind of data transmission. All we got was constant radio silence. But when I started turning the oscillator on and off by hand, I was able to send out messages in Morse code. The process of manipulating the carrier wave to carry useful data is called modulation. And there are many ways you can manipulate a carrier wave, but one of the easiest to understand is amplitude modulation. AM allows you to send an analog signal, like your voice, over long distances. It works like this. Here's your carrier wave, a continuous wave of, say, 1 MHz. Here's a lower frequency voice signal, let's say a sine wave of 500 Hz for now. Now, if I create a circuit that uses the amplitude of the voice signal to vary the amplitude of the carrier wave, I will have amplitude modulated the carrier wave. And more realistically, this is what it would look like with voice or music. So let's take a look at a circuit that can do this. The first half is the oscillator that you've already seen. It generates the carrier wave, which is a continuous high-frequency sinusoid. Over here we have a high-pass filter to remove the DC offset from the oscillator's output. The high resistance of 100K also helps to isolate the oscillator from the modulator, so that the modulator doesn't mess up the generation of a frequency-stable carrier wave. Over here we have another high-pass filter to ensure that we're only getting AC audio from our MP3 player or other audio source. Finally, the op-amp circuit on the right will take the audio signal from my MP3 player and use it to dynamically adjust the amplitude of the carrier wave. The potentiometer on the left controls the amount of modulation, and it also provides a DC operating point for the circuit to work at. And once we have that amplitude modulated signal, you can hook it up to an antenna and some of the energy will radiate out in the form of radio waves. Okay, let's hook up the MP3 player and start modulating the carrier wave. My oscilloscope will be displaying the voltage right at the modulator's output, before the antenna. And there you have it, a simple AM radio transmitter. Also, if we zoom in on the amplitude modulated signal, we can see that it's still based on the 950 kHz carrier wave. This is a very low-powered, unoptimized design, so don't worry about any legal issues. It's only going to have a range of a couple of centimeters. If you want a little bit more range, add a 220 microhenry inductor in parallel with a 100 picofarad capacitor over here. What this will do is cause the current in the antenna to resonate, which will result in more energy being turned into radio waves. I'll do a video on LC filters and resonance in the future. Finally, I'd like to thank Stefan0719 for the circuit designs used in this video. Check out his channel for more great circuits.